Or good morning, everyone. We're here today for the Statistics Former Student Network webinar. Our speaker today is Dr. Yehua Lee. Dr. Lee is a professor and chair of statistics at the University of California at Riverside. He received his PhD in statistics in 2006 from our famous Texas A&M University under Dr. Raymond Carroll and Talon Singh. Before joining the University of California at Riverside in 2018, he held faculty positions at the University of Georgia and Iowa State University. He is a fellow of the American Statistical Association, a fellow of the Institute of Mathematical Statistics, an elected member of the International Statistical Institute, and a recipient of the National Science Foundation Career Award in 2012. He's served on the editorial boards of the Canadian Journal of Statistics, the Journal of Multivariate Analysis and Statistics, and his research interests include functional and longitudinal data analysis, non- and semi-parametric methods, spatial statistics, measurement error, and mixture models. Dr. Lee was also a recipient of the H.O. Hartley Award. So let's all give him a good welcome and let him take it away. Thank you, Dr. Lee.
Thank you so much for the nice introduction. It's good to be back. Good to get connected with former graduate students. In the introduction, I graduated in 2006, and really looking forward to get back to College Station next year for Ray's birthday conference. This is a recent work with a visiting PhD student at the time, Kun Huang. I know I see him in the audience. He's doing a postdoc at Texas A&M with Huiyan now. And another co-author is Yuntao Guan, also alumni of Texas A&M. He was 2 years ahead of me. We worked on many projects on the intersection of functional data analysis and the point process. I know Yuntao gave a talk maybe a year ago on different classes of point process. So this is a more recent work. I hope we can present this in friendly audience and give us a few nice feedback to help us to get this work over the publishing line. So we're going to talk about spatially and temporally indexed point processes. I'm going to do functional data modeling, do principal component analysis. This talk also has something to do with partially linear single index model. I know Hua Liang gave the previous talk last month. He talked about different classes of semi-parametric regression models. But I believe in his abstract, he was focusing on partially linear additive model. I'm using partially linear single index model, which add to the long list of semi-parametric models. I started working on partially linear single index models when I was working with Naixin Wang and Ray Carroll at the time. And I was mostly using kernel type of methods, but now Kun is the leading author on this paper. He's an expert in spline, so this time we're going to do splines. Okay. So brief outline, I will give an introduction, motivate the methodology, then we talk about the model and the estimation procedure. Then we will talk a little bit about asymptotic properties. And for the interest of time, I'm going to skip any simulation study, just finish up with some data analysis. Okay. So point process models aim to model the pattern in location and time of certain events of interest. These kind of models are widely used in business, ecology, epidemiology, seismology, and transportation science. In another project, Kun is working on modeling the location and time of wildfires within the United States. So it's widely used. More recently, there are applications where you have point processes. There are spatial and temporal index. So basically, I'm looking at spatial and temporal data, but each data point is a point process within the day. Okay. Repeated measured stochastic processes are usually modeled as functional data. Here I list the two papers on independent functional data, where you consider random curves as realization of a stochastic process with a Kahuna layoff expansion. The last paper here, Zhang and Li, I presented this work in Texas A&M back in 2019. That was the last time I back to College Station. Really get a lot of good feedback, help us a lot, and took us another 3 years to get it published. We also have some previous work on modeling point process data using functional data analysis approach. Basically, for point process data, you got to model the intensity function. And if you have many point processes, a whole collection of point processes, you can use latent process to model the difference between these intensities. And these latent processes can be modeled using functional data analysis approach. Okay, the motivating data in this paper, couldn't find this. We're using the bike sharing data as an illustration, but obviously the methodology can be widely used in many other areas. So the data come from Citybike. This is a company for bike sharing, largest bike sharing system in the US. And they have their network of bike sharing stations in many big cities in the US, I believe. And we are focusing on the bike stations in New York City. And we're only focusing on the data collected in June of 2018. So there are the data were collected from over 400 stations and over a month of time. And each data point we consider is the intraday bike sharing pattern. So for each trip, we have record for their departure station, the date, and the time within the day. So we're modeling the departure time within the day as my point process. In addition to the trip information, we also have some important covariates collected. For example, temperature of that day, population density near that station, etc. So all of these can be helpful in modeling the intensity of these events. Okay. So you can imagine this kind of modeling eventually can be applicable to many kinds of business-related applications. So couldn't put these the stations on the map of New York City as an illustration. So you can see this is a Manhattan Island, and there are many dots on this map. Each dot represents the location of one bike sharing station. There are 400 of them, and the color or the rescaled number of total trips within that month. So all those yellow dots, they're hot spots. These are the stations you see a lot of trips. So overall, you can see along the Manhattan Island, there's a spatial trend. So we put these 3 bars, these artificial bars, they mark the location of the 14th Street, 34th Street, and 59th Street. So basically, beyond the 59th Street, that's classically called uptown, and below 14th Street, that's downtown. Somewhere between, you get the midtown. So we further classify that as upper midtown and lower midtown. So there's a spatial trend going on here. You see less activity in uptown, and most of the trips concentrate in midtown. So there's a trend along this avenue direction. Okay, that has to be considered later into the modeling. some more summary of the data. So you have 400, the first plot, you have all these stations. Obviously, there's a lot of variation for the total number of trips among these stations. Some of these stations have up to 14,000 trips during the months. Some of the stations, there's a lot less activity. And also you can summarize the trips by day. So you can see, if you look closely, there is a 7-day periodical pattern going on. So weekday, weekends, they have different pattern. You can also summarize, just put the data together, estimate the intensity of trips within a day. Okay, so you can see there are 2 peaks correspond to within the same day from 0 to 24 hour. So there are 2 peaks correspond to the 2 rush hours. So there are a lot of patterns in this data. Okay, so let's summarize the data structure. Capital Nij is a collection of time points. This is the point pattern we're talking about. This is the intraday back-sharing activity. So the time points are the else trip from station I on day J. We're just modeling this time within a day. Okay, and little n is the number of stations. We have 410, and capital N is the number of dates. For now, we focus on within 1 month. So capital N in our data is 30. Obviously, you can collect more data. Okay, so we're gonna use log Gaussian Cox model to model this kind of point process. So you can see these point processes now are indexed by spatial location and date. Okay, so Nij, we're going to assume it's a conditional on some covariates and latent processes. It's going to be a Poisson process. And the log intensity function is given by this log linear model. Any questions in the audience? Okay, so there are different parts. Mu is the log baseline intensity function, and this linear form is a partially linear form. W is an observed vector of covariate, and U is another collection of observed covariates, but there might be some nonlinear effect. So the third term here is a single index structure. Okay, so theta is suppose the dimension is D1 is the partially linear coefficient vector, and the beta, suppose the dimension is D2, is the single index coefficient. And we also have 3 latent effects. These effects are X, Y, and Z, representing the effect of station, the day, and the station by day interaction. Okay, T here, again, is the time within a day. So you can scale the time, the 24 hours into a 0-1 interval. So time, T is the time within a day. Okay, so these latent effects are also indexed by time within the day. So they become stochastic processes. And we're going to assume they are zero mean latent Gaussian processes. We're going to assume they are independent among them. X are independent of Y, independent with Z, but X themselves, because these are effects of locations, but they could be spatially correlated among themselves, among the X's. Okay. So we're going to assume all the X processes are spatially correlated across stations. Y's are temporally correlated across days. Zij, these are interactions. We're gonna assume they're independent among themselves. And the three effects are mutually independent. Okay, so the next paragraph I get from Ray Carroll's interpretation why we're gonna use partially linear single index model. This is from his famous 1997 JASA paper on generalized partially linear single index model. Sum up quite well why do we use this kind of structure. So this structure, partially linear single index, is a good compromise between interpretability and the flexibility. So W include the covariates that are important for model interpretation and linearly related to the log intensity. U, on the other hand, contain the covariates that are nonlinearly related to the intensity function. Single index structure is used a lot in the econometrics literature, and mostly to avoid the curse of dimensionality. This is a very widely used model. However, to the best of our knowledge, has not been used before in modeling point process data. Okay. There's a classic identifiability issue in this kind of seven parametric regression. So to make the model identifiable, we need to assume the single index coefficient has norm equal to 1. And again, make it identifiable, assume the last component of the single index coefficient is greater than 0. Okay. Also, in order to identify mu and g, in order to make them distinguishable, we have to assume the mean of this single index structure is equal to 0. Okay, so there are a lot of constraints. So now let's continue to model these latent processes. These are temporal processes indexed by time within the day. So we're going to assume there are L2 processes, and you have the classic Kahuna-Lioff expansion. So these are infinite expansions. For example, X can be written as infinite expansion of these principal component scores and the eigenfunction multiplied by the eigenfunction. So Y and Z have similar decomposition. The three sets of eigenfunctions are orthogonal within their own group. Okay, the three processes X, Y, and Z, they're independent between across the group. Right. The principal components for X are zero mean Gaussian random variables with variance eta xk. Okay. Right. And we're going to assume the principal component scores are spatially correlated. Okay. Likewise, the principal component score for the Y process, these represent the time effect. So assume there are zero mean Gaussian variables with variance eta ky, and you could have temporal covariance among these scores. Okay, so it's a very complicated structure. With that, you can write out the spatial temporal covariance for the X process. Any questions in the audience? Okay, so for now, we're going to assume stationarity. Well, this expression looks like it's a spatially stationary and isotropy. This is only for simplicity, can be relaxed. So for now, we're going to assume the spatial temporal covariance for X is a three-dimensional function, and can be written as with this collinearity co-regionalization model. So it's an infinite sum of these separable structures, which are a spatial covariance multiplied by some temporal covariance. The temporal covariance is not necessarily stationary. Okay. Similarly, Y process have this three-dimensional covariance structure, again, with similar structure. Z processes are independent, so they have a two-dimensional covariance like this. This is similar to the classic functional data setting. Okay. So because these three processes are latent, they represent the station, day, effects, and their interactions. So you can also define the so-called marginal first order intensity. Well, it's still conditional on the covariance, but we want to marginalize over the unobserved latent processes. So the expectation here is only taken over X, Y, and Z. Now, using the Gaussian property, now you can see the intensity function becomes this. It's the partially linear single index structure of the covariance plus this non-parametric function gamma t. Gamma t now is the baseline log intensity function plus the variance function of the latent processes. So just looking at the first order intensity point of view, there's no way to distinguish mu versus all the other variance functions. So we have to model gamma as a whole function, as a whole thing. Okay, so it's possible to fit a generalized partially linear single index model using the first order intensity function. Okay, now to dive into the detailed structure of these covariances, we have to look at the second order intensity, which is a point process equivalent of correlation function. Okay, so now we are looking at a data indexed by I, J, and T. Again, I is the index for station, J is the index for day of the month, T is the time within that day. Okay, so for two tuples, IJT T1 not equal to I prime J prime T2, you can define the second order intensity function. So in other words, there are two trips happened. One happened at IJT1, the other trip happened at I prime J prime T2 simultaneously with the chance given this way. Okay, so again, this expectation is taken over the random effects. So as a result, the second order intensity is the first order intensity at IJT1 times the first order intensity at I prime J prime T2 multiplied by exponential of these three covariance functions. Okay, the covariance of X, that building the spatial information, covariance of Y, introduce the temporal covariance, and the effect of Z play a role only if we're talking about same station, same day, but at the two time points. Okay, because the Z processes are independent among themselves. If we are talking about a different day or different station, either of those cases, then effect of Z will be eliminated in this equation. Okay, so using that, later we're going to build an estimation procedure to estimate all these covariance functions. Okay, so the parameters we need to estimate, there are a lot, and there are a number of challenges here. First, we do functional data modeling of the latent processes. So all these covariance structures are non-parametric. We make minimal model assumption on the covariance structure. We use the Calhoun-Lioff expansion. All the eigenfunctions are left to be non-parametric, and you need to estimate them. Second, as you can see, there's a very complicated spatial temporal correlation structure that not only complicated the estimation procedure, also give us a lot of challenge in developing theory. Third, this partially linear single index structure, which is a typical semi-parametric modeling. There is a lot of challenge associated with that, and this is now combined with the other challenges, just give the difficulty to a different altitude. Okay, so we're gonna do the estimation in 2 steps. First step, we're gonna use the first order intensity function, trying to estimate all these mean effects. Okay, the first order, the coefficient and the unknown functions in the first order intensity. In the second step, we're gonna use a composite likelihood approach to estimate all the functions involved in the second order intensity function. In other words, these covariance of these latent processes. It's a very complicated procedure. Okay, so for first order intensity estimation, we're gonna use a maximum Poisson likelihood approach. To me, even though the real model here is a log Gaussian Cox process, it's not real Poisson, but the Poisson likelihood to me is like a least square or quasi likelihood in the point process setting. So as long as you can correctly specify the first order intensity function, you get consistent estimator. Okay, so we're gonna use, this is the marginal first order intensity function we just mentioned. It depends on the link function for the single index structure, the function gamma, the partially linear coefficient, and the single index coefficient. So for all of these. Okay, so this is a Poisson likelihood. Basically, it's the log of the first order intensity function evaluated at all the event time across all station, all date, and all the events within that day. Okay, and minus the integral of these intensities. Okay, so you can show if you take a derivative of this function, the score is unbiased. Okay, that's all. Give you an unbiased estimating equation. That's all we care about. Now, because Quinn is the leading author and he likes to use splines, in order to estimate this function g, we have to define a spline basis to do that. So for convenience, we do a little bit of transformation for this single index structure. So u times beta, we have to transform that to an interval, to the 0-1 interval, so that we can define spline basis on the 0-1 interval. This is just for convenience. I believe the transformation Quinn used was kind of a gamma CDF type of thing. So there are typical ways to do that. Now, instead of modeling G, we model this G delta directly. And you can model that as spline. In fact, we're going to model G delta. G delta is a function on 0-1 interval. Gamma is a function of the time within the day. We scale the time into a 0-1 interval as well. So both of these can be approximated using B-splines. So if you plug all these things into this model, and this likelihood become parameterized, and you can maximize the likelihood. Second order intensity is more complicated. We're going to build a likelihood based on the second order intensity. Somewhat is similar to what we did for the first order intensity. It's also based on the log of the second order intensity and minus the integral of the second order intensity. In some way, it's similar to the Poisson likelihood, what we did for the first order intensity. But now we're talking about the pairs of events. Okay, so we're talking about the pairs event at ij time L and another event at station I prime, day j prime, and time L prime. So we are talking about all these pairs, and there are incredible amount of number of pairs, right? If you have tens of thousands of events overall, if you're talking about all the pairs, that could be millions, right? So you have to narrow it down. You have to, a lot of these pairs do not provide enough information at all. You have to downweight them. So that's why we also introduce these weights. They can be very, very useful. Just to remind ourselves, the second order intensity look like this. And it has something to do with the first order intensity at those two time, and as well as the covariance between those two time, two location, two dates. Okay, weight function are to be specified. Like I said, it's a very complicated procedure. We're going to adopt a different weight function for estimating different terms. For example, if we are trying to estimate the covariance of X at a zero distance, in other words, we're talking about the covariance within the same back station. So to estimate that, this is the weight function we're going to use. We're going to focus on those pairs that I is equal to I prime. In other words, we're talking about pairs of events happened within the same back station. But for two dates that are at least delta y days away, so that delta y is a tuning parameter, so that 2 days they're far enough so that the temporal covariance become diminishing, can be ignored. So the effect of y essentially can be eliminated from this. And you're talking about the point process at the two different dates, so the z effect is also diminishing from the equation. Also, we want to downweight using the first order intensity. This is just for convenience, because of the way we're using this in the composite likelihood. The second order intensity has all the first order intensity in it, and this is almost like a inverse intensity weighting. So we'll just cancel out these first order intensities, simplify the equation a lot. Okay. Similarly, we can estimate the covariance of y, covariance of z, using the same composite likelihood, but adopting different kind of weights. To estimate the y effect, we're gonna focus on those pairs that are from two stations that are at least a delta x away, so that the spatial correlation is ignorable. And we're focusing on pairs of events happened on dates that are p legs away. Okay, again, we're going to downweight the first order intensity at those 2 points. Estimating z, we are focusing on pairs of events happening at the same time, same day, same station, same day, but different time within that day. And all these functions are bivariate smooth functions, we're going to use them, approximate them using tensor product of B-splines. Noticing that the station effect, covariance of the station effect, when the spatial lag equal to 0, it has a spectral decomposition like this, and the part of the model is about these eigenfunctions and eigenvalues. So we get an estimate of this. We can do a spectral decomposition and get all the eigenfunctions. This is done by solving an eigenvalue decomposition equation. Because the covariance is registered as tensor product spline, so it has been parameterized. The problem can be reduced back to a multivariate PCA problem. We can solve this using the typical Ramsey and Silverman approach. Similarly, you can decompose the covariance of Y, the covariance of Z, get their eigenvalues and the eigenfunctions. Even though in theory, you can have infinite number of principal components, but in reality, you have to truncate them. The number of principal components admitted in these models can be selected using so-called percentage of variation explained approach. Now, we also have to estimate the spatial covariance among the principal component score of the X process. We're going to model them using Matern covariance. So they're registered by some unknown coefficients, unknown parameters. So now by plugging the estimated eigenfunctions in, the three-dimensional covariance function for the X process now can be written in this way. It is known up to a few unknown parameters. All you have to do is to estimate these spatial covariance parameters. Now we're gonna use the composite likelihood approach again, because the second order intensity function tell us everything we need to know about the spatial correlation and the temporal correlation. So this time we're gonna have various components of the model already estimated. We're gonna plug in their estimators. The only thing unknown at this point are these spatial covariance parameters, and we're going to focus on estimating those parameters. You can also estimate the temporal covariance of Y. I'm going to get into that. Again, a lot of equations, not going to get into the details. The principal component scores are latent Gaussian random effects. In order to get an estimate of those, we're going to maximize the posterior distribution. So we're going to use their conditional likelihood. Now, because, for example, this is the cosine X is the truncated principal component score vector. It's truncated because in theory it's infinity, but we only keep the first px principal components. So as a result, this is a vector with little n times px. That's the dimension. So that's the number of latent effects we are trying to estimate. The first part of this posterior, this is a log posterior. The first part corresponds to a Gaussian distribution. Now, the estimated spatial covariance information now serve as a prior in this posterior. So you can use it to regularize the estimate of these principal component scores. Rest of this is from Poisson likelihood, because conditional on these scores, the point process are assumed to be a Poisson process. Okay, so maximize this, you get a predicted score for the X process. Similarly, you can do this for Y, for Z. It's just a lot of algebra. My procedure depends on a lot of tuning parameters because I have to choose the number of splines. So we do cross-validation. Basically, you have spatial and temporal data. You have to divide the data into different blocks. So take out one block as validation, use the rest of the data to estimate the parameters, and then use the likelihood within this block to do cross-validation. Okay, not going to get into details, but there are cross-validation procedures to choose the knots for the first order intensity estimation. For the second order intensity estimation, you still have a lot of tuning parameters. The estimation is based on composite likelihood, so you can build a cross-validation based on composite likelihood as well. Again, not going to need to get into details. Very briefly about asymptotic result. We're going to assume the spatial dependency among these latent processes X, the temporal dependency among Y, and the spatial temporal dependency among these covariates. We assume they can be quantified by some alpha mixing coefficients, decay exponentially. We're gonna in our framework, we're gonna assume the number of station little n, the number of days capital N, both diverge to infinity. To do that, essentially we're saying both of these are indexed by little n, and assume the number of days is diverging in order, in a polynomial order of little n. We have to assume all the functions we're trying to estimate satisfy certain smooth conditions. There are many of them, not going to list them all. The number of knots, there are so many of them, they have to diverge to infinity. Very technical paper. And with a certain rate, all of these are specified in a paper. The likelihoods, their score, their Hessian satisfy some regularity conditions. All of these are necessary. Okay, so first we developed the asymptotic normality of the parametric component. So the parametric components included the partially linear coefficients and the single index coefficient. Because the single index coefficient have a constraint to it, so usually to get rid of the constraint, you can eliminate the last component of beta. This theta minus is essentially theta, but without take out one of the coefficients. Knowing the first D2 minus 1 beta coefficients, the last one can be solved using the unit norm constraint. So there are only D minus 1 free parameters here. And the regularity conditions, we developed this asymptotic normal distribution. But what's new here? I want to point you to this point here. The effective sample size, it's asymptotic normal, but what's different here is we show the effective sample size under the correlation structure we're considering is small n times capital N divided by the sum of the two. Okay, so this is very, very different from a typical spatial temporal data under weak dependence. Under typical weak dependence covariance structure, you would assume the correlation will decay in a three-dimensional distance. So spatial and temporal, you have three-dimensional indices. Either spatial lag or time lag is large enough, then the correlation would be diminishing, right? But in our setting, all the all the data collected at the same station would share the same station effect. No matter how many days these processes are apart from each other, they share the same station effect, then they will be strongly correlated to each other. Similarly, all data, no matter how far these stations are away from each other, their back sharing records within the same day would be strongly correlated because they share the same day effect. So there's a factorial structure in our model. Okay, so there's a very subtle point here that the spatial temporal covariance is diminishing only if both the spatial lag and the time lag are large. So have to be stations far from each other and have to be 2 days far from each other, 2 very different days. Then the two processes would be approximately uncorrelated. So very stringent condition. It's a very strong correlation structure. That's why the convergence rate is quite different. And also we find this effective sample size is somewhat in the same order as the minimal of little n and capital N. Okay, so means so the convergence rate is determined by the smaller number of the two. You need both the number of stations and number of days to diverge to infinity in order to have consistency. Okay, all right, so convergence rate for the non-parametric functions in the first order intensity. I'm not going to comment on that. Just a lot of theory. Convergence rate for the covariance from the composite likelihood. Again, a common theme in all this theory is that the effective sample size is determined by the factor small n times big N divided by small n plus big N. Okay, so consistency for the eigenfunctions, consistency for the principal component scores. So we develop all of that. What's surprising is we went through a first round of review at JASA, and one of the referee asked, you got a very specific application. Why didn't you send the paper to JASA application and case study? After all the theory we presented, so that's a very amusing comment. So let me jump to the data analysis part. Try to wrap it up really quickly. So again, we are focusing on the bike renting events happened in New York City. You have 400 stations and 30 days. But for each day, each station, we also have these spatial temporal covariates considered. For example, temperature of that day, temperature of that time, indicator for rain of that day, indicator whether that's a weekend day. The mean population density within the range of 18 to 62 years old in that neighborhood. The median income in the neighborhood of the station. Median population age within 1 kilometer of each station. The number of stations within 300 meters of the station of interest. So a lot of covariates. If you recall, I mentioned that there's also a spatial trend running along the axis of the Manhattan Island. So in order to model that spatial trend, we also threw in a few spline bases just to model the spatial trend. The argument U is the scale distance from the bottom of the Manhattan Island to that station I along the direction of the Fifth Avenue. Okay. So in this case, the indicators, in other words, indicator for rain, indicator for weekend, these are considered to be the linear part, and these spatial trend bases are also included in W, which is the linear, partially linear part. The rest of the covariates are thrown into this single index structure. We do estimation, and to make inference, we did a parametric bootstrap. We did 2 versions of it. One version we consider X to be spatially correlated. The other version just totally ignore the spatial correlation. Okay. First graph here is the histogram for the single index structure. Okay, U transpose beta. So this is the second graph. Part B is the estimate function for gamma C is the estimated link function G. There's a little bit of nonlinearity going on. And D is the estimated spatial trend along the Manhattan Island. So you can see, just like what we observed, there's less intensity, less activity in uptown, more intensity in downtown and midtown. These are the estimated coefficients in my model. So the bold ones are significant based on our bootstrap. So weekend has a significant effect. So for weekend days, the coefficient is negative. That means there's less activity. And this is based on the standard error we have, it's significant. Median income in the neighborhood has a positive effect on the bike renting activity. Median age also has a negative effect. So older population, less bike renting. Okay, so this is all making sense. The other ones are insignificant. So we also try bootstrap without spatial correlation. Most of the time, you underestimate the standard error, sometimes it leads to wrong inference. Okay, we did a second order estimation to principal component of the latent random effect. Based on percentage of variation explained, we choose 2 effects for the X process, 1 effect for Y, 3 effect for Z. For the X process, we assume the spatial correlation is this exponential correlation structure. Based on the estimated range parameters, we concluded that the spatial correlation is close to 0 when 2 stations are 3 kilometers or more away from each other. Also, the temporal correlation diminished pretty fast. So 2 days, at least 3 days away, there are almost no temporal correlation. Okay, so very weak dependence. These are the estimated eigenfunctions. Because of time, I'm not going to get into details. The first principal component of X is above 0. That means apart from the estimated mean function, the first order intensity, if a station has high loading on the first principal component, it will have an overall higher rate of a bike renting activity. Okay, and second principal component, there's a contrast between night and the day. So the stations with high loading on the second principal component will have a lot of nightlife. During the night, there will be more activity and less so during the day. So Y principal component have this structure. This is the day effect. So those days with high loading on the first principal component Y, that means it will have less of a peak during the rush hour. So those days happen to be the weekend days. Okay, so all of these are interpretable. So estimated principal component score for the first component of X, map them into the Manhattan Island. And these are the estimated score for the second principal component of X, mark them onto the map. So we also have the trajectory for the principal component scores for the day effect and plotted over the dates. You can clearly see there's a 7-day cycle going on, right? So clearly the principal component here model the weekend weekday effects. So we thought that these results are really neat. So summary, I'm using the whole hour. We have proposed a new model framework for spatial temporal index point process data. We introduced this semi-parametric, partially linear single index structure to model the effect of spatial temporal covariates, providing a good balance between model flexibility and interpretability. to account for unobserved spatial temporal random effects as well as their interactions, we introduced 3 latent functional effects and allow the spatial function effects to be spatially correlated, the temporal effects to be temporally correlated. Our theory requires a new asymptotic paradigm because of the complicated correlation structure. The effective sample size is dominated by the minimum of the number of stations and number of days. You need both small n and capital N diverge to infinity in order to achieve consistency. So we thought that that's a very neat result. So here are some of the references. Thank you very much.
Thank you, Dr. Lee. Are there any questions from the audience? You're so thorough, no questions.
My co-author is in the audience, so I don't know.
Yeah.
In a year's time, I think he's gonna look for a job. He's a postdoc at Texas A&M. He's working with Huiyan Sang right now, working on new projects, I'm sure. But we're revising this.
That's awesome.
Yes.
Okay, we'll keep the floor open for just a couple more minutes. It's not quite noon, so we can see if there's anyone else who wants to chime in.
Sorry, I'm stopping you from lunch.
Yeah, no, I think it's fine. I think we still have a couple more minutes if anybody has any questions. Just don't want to rush anyone. I don't see anybody.
Really good to be back, and hopefully this can help us broadcast this work a little bit. We are revising this. The referees ask us to compare with some benchmark models. Quinn is doing that. I want to say we are, but Quinn is doing all the work. So hopefully, if you have any comments, suggestions, let us know. It's very difficult to publish such a complicated procedure, and referee seems a little bit confused. So if you have any suggestions, how do we present this thing better? I know it's a very long talk, a lot of technical details. That maybe the referees also can find that very confusing. So anything can help us to improve this work, let us know.
Awesome. Well, thank you so much. Last call for questions. Anyone else have any questions or maybe even a comment they'd like to make before we end today's presentation?
Well, thank
Well, thank you so much for presenting your work, your joint effort with your friends, and we really appreciate getting to know what some of our Aggie friends are doing out there in the community.